Hello everyone, welcome to this 20th lecture of the NPTEL course on Riemannian geometry. So let me just quickly recall what we did in the previous lecture. We introduced curvature for the first time. From now on I am going to look at Riemannian manifolds Mg, and all the connections that I am going to talk about are going to be Levi-Civita connections. So we have a Riemannian manifold Mg, and we consider the Levi-Civita connection of that Riemannian manifold. Then the Riemann curvature endomorphism was defined in the following way. We had R of xy acting on z is essentially the commutator of the covariant derivatives acting on z, but then you also needed this correction term coming from the Lie bracket. The reason why one needs this correction term, let me remind you, is so that we get C infinity linearity. The advantage of that is that one can then think of R as a 1,3 tensor. Okay, so in particular what this implies is that one can localize and talk about the curvature endomorphism at one point as basically a multilinear map on the tangent space. Okay, so then with this Riemann curvature endomorphism, we also defined this other thing called as the Riemann curvature tensor, which has this definition. Locally you can write R as Rijk upper L times epsilon I tensored epsilon j tensored epsilon k tensored EL, where EI's are some local frame and epsilon j's are the dual frame. Similarly, Rm being a 0,4 tensor, so this is a 0,4 tensor, again because of C infinity multilinearity of R. You can express Rm as R lower Ijkl times epsilon I tensored with epsilon j tensored with epsilon k tensored with epsilon L, and the way these two are related is that they are essentially related by lowering and raising of the indices using the metric, right. So both the curvature endomorphism and the curvature tensor essentially denote the equivalent quantities up to lowering and raising indices. Okay. So we'll speak, whichever is convenient, we'll either consider the curvature endomorphism or the Riemann curvature tensor. Alright, so maybe I should begin with a sort of cautionary note. That the convention we have used for the curvature that we have used is actually common but not universal. So some textbooks, example, if you look at, I think Docarmo's Riemannian geometry or Gallo's Riemannian geometry with his co-authors Gallo et al. These textbooks actually use a different convention for the curvature endomorphism and tensor. So let me maybe briefly explain that. So in some of the books, instead of the commutator of nabla x and nabla y, you would define the curvature endomorphism as the commutator of nabla y comma nabla x, and then of course the Lie bracket term will also be y comma x rather than x comma y. So that means that the curvature endomorphism in those textbooks is off by a sign. So is the same as our curvature tensor, except it will have is the negative of our curvature tensor. Right. Similarly, some textbooks have a different convention for the 0,4 curvature tensor. So whenever you are reading a new textbook on Riemannian geometry, you should always look carefully at what their convention is. Okay, but whatever the convention is, later on we are going to introduce these notions of sectional curvature. Much later we are going to introduce a notion of Ricci curvature and scalar curvature. So whatever convention of curvature that you use, eventually everyone in the world agrees with what sectional, Ricci and scalar curvature means, okay, which is convenient because many of the theorems in Riemannian geometry are statements of the kind that if the sectional curvature or the Ricci curvature of the scalar curvature satisfies a certain property, then your Riemannian manifold satisfies a certain property, right. So there, if people did not agree with the conventions, it would be chaos, right. So just to repeat, everyone in the world agrees with what sectional curvature means, what Ricci curvature means, what scalar curvature means. The only difference in convention comes when one talks about the Riemann curvature endomorphism and the Riemann curvature tensor. So whenever you open, as I am repeating myself, whenever you open a new book in Riemannian geometry, always be careful of what convention the authors are using, okay. Alright, so with this sort of cautionary note, let me begin this lecture. So the goal of this lecture is to discuss some important properties of the curvature tensor. So we want to discuss some symmetry properties and Bianchi identities, okay. Alright, so the first proposition is the following. So maybe let me, because it's a longish proposition, let me write it on the next page. So here's the proposition. So let x, y, z, w be vector fields. Then we have the following. So if you take the endomorphism R applied to x comma y, so as I said last time, this defines an endomorphism. If you localize at a point P, this defines an endomorphism of the tangent space. Otherwise, it takes in a vector field and spits out another vector field. This is skew-symmetric in the sense that if you interchange y and x, you would incur a negative sign. And of course, similarly for the 0,4 tensor. The second property is skew symmetry in the other two entries. So R of xy as an endomorphism is a skew symmetric endomorphism. So what that means is if you apply Rxy to Z and take the inner product with W, that's minus the inner product of Z Rxy applied to, let me write this out clearly. This is minus the inner product of Z times Rxy applied to W now. So the point is, suppose R of xy were a symmetric endomorphism with respect to the inner product, then that means that if you transfer this here, you would get the same answer, right? But in this case, it turns out to be a skew symmetric endomorphism. That's why you incur a negative sign, okay. So then in terms of the 0,4 tensor, this just means that if you interchange the final two entries, you get a negative sign. Okay. So the third point is the first or algebraic Bianchi identity. Okay. what that means is the following. So R of xy applied to z plus you cycle through these indices. So you put z here, x here and y here. So that just means R of z comma x applied to y, and then you again do the same thing, R of y comma z applied to x, that is going to be 0. Okay, and you can write down a similar expression for Rm. And the fourth is some kind of a symmetry that if you take Rm of xy zw and you take these two and interchange the pair, then this is going to be Rm of zw xy. Okay, so in local coordinates, or in local frame, the symmetry and anti-symmetry relations, so and skew-symmetry, so they are basically 1, 0.1, 0.2 and 0.4 can be written succinctly as this. So R of I j k l is R of j I k l. So you are interchanging the first two entries. That is the same as minus R I j. You are interchanging the last two entries L k, and that is the same as R of, you interchange the first two with the last two. So R of k l I j. Okay, and the Bianchi or the algebraic Bianchi identity can be written in the following way, that R of I j k l plus R of k I j l plus R of j k I l is 0. Okay. All right. So locally, I mean, this is what the symmetries, anti-symmetries, and the Bianchi identity mean. So I'm going to actually leave the proof as an exercise, but I'm not going to completely leave it as an exercise. Exercise using the next lemma. So I'm going to state a lemma which essentially gives a formula for these things. Using that, it's actually quite easy to verify this proposition. Okay, so I'm going to prove the lemma completely, but the proposition I'm going to leave it as an exercise. All right. Okay, so what is this lemma? Okay, it has two parts. So let x1, x2 up to xn be local coordinates centered at some point P in M. Then our curvature tensor has an explicit expression in terms of the Christoffel symbols. Sorry, this should be upper L. So I'm looking at the components of the curvature endomorphism that has this nice explicit formula. ISL gamma S JK minus gamma IKS gamma JSL. Okay, so schematically this is some derivatives of the Christoffel symbols plus something that involves a quadratic term in the Christoffel symbols. Okay. Right. The second part is what happens in normal coordinates. So let now x1 up to xn be normal at this point P. Then if you look at the zerofold tensor at the point P, one has the following formula. So it will be del squared g I k by del xj del xl. So maybe let me I need more space. So this is del square g I k by del x j del xl plus del square g JL by del xi del xk. So all of this is of course at P minus del square G IL by del xj del xk at P minus okay. So using this lemma you can easily prove the proposition on symmetries and the first or the algebraic Bianchi identity. Okay, so how do you prove the lemma is just a calculation. So let me prove the lemma. Let's look at the first part. So from by definition if you look at the commutator of del I del j, since if you take the standard basis vectors then their commutator, their Lie bracket is 0, right. So the curvature del I del j applied to del k is simply this commutator applied to del k, right. Okay, but on the other hand this is also by definition just R I j k upper L times del L. So in order to calculate, in order to find a formula for this, I basically have to calculate what this is. Okay, so let's do that calculation. Okay, so the commutator of these two applied to del k is this del j applied to del k minus del j del I applied to del k. Okay, so let's look at the first term. So that's del I applied to del j applied to del k, but by the definition of Christoffel symbols that's just gamma jk L or gamma jk S times del S. Okay. Then by C infinity linearity, when you try to find the covariant derivative of this, you would firstly have del I acting on the Christoffel symbols times del S plus gamma jks, the covariant derivative of del s. Again, the covariant derivative of del s can be expressed in terms of Christoffel symbols. So that's del I gamma jk s del s plus gamma jk s gamma I s l del l. Okay. So now I want to combine these two terms. So I simply change the s index here to l. I mean, this is just some index, right? So I am free to rename my indices. So if I do that, I get the following formula. That this is simply del I gamma jkl plus gamma ISL gamma jk s times del L. Okay. So similarly, the second term I can do a similar calculation. And I end up with the following plus I just replace wherever I is there, I replace it with j, wherever j is there, I replace it with I in the formula for the first term, right? Because okay, and now if you subtract these two, that's exactly, you get what I was claiming in the lemma, right? So just subtract the two. Okay. All right. So that proves the first part. Now let's see how things simplify if I'm using the normal coordinates. So now in normal coordinates, we have that at that point all of these are 0, and in fact because of this the Christoffel symbols are also 0 for all I, j, k. Now consequence of this is that if you take the inverse of the metric components, so if you take g upper ij and differentiate that, that is also going to be 0. Okay, why? That's because of this reason that abstractly this is a calculation that hopefully you have seen in a multivariables course, that if you have a invertible matrix A which depends smoothly on some parameter, you differentiate the inverse with respect to that smooth parameter. In other words, let me maybe make things more concrete. Suppose A is a smooth path in GLN, then d by dt of A of t inverse. So you take A of t, you take the inverse, and now take the component wise derivative. That's the same as A of t inverse times d by dt of A times A of t inverse. So if this thing is 0, if the derivative of the matrix is 0, this will imply that this is also 0. So that's the same sort of thing that happens here. At the point P, the derivatives of the metric components are 0. So at the point P, the derivative of the inverse of the metric components are also 0. Okay. So we'll use this. So now in normal coordinates, if you look at the formula from part 1, so part 1 implies remember that that you had the following formula. Plus something that is quadratic in gamma, right? Okay, so that means at P, because gamma P, all the Christoffel symbols are 0, this would imply that R ijkl at P is simply given by this. Okay. So in order to prove my formula in normal coordinates, I only have to calculate what these are. Okay. So let's do that in the next page. Right. So right. So let's calculate what this is. So our goal is to compute del I and del j of gamma ikl at P. Okay. So for that, I recall the definition, recall a formula for the Christoffel symbol. So recall that gamma jk, right, so, sorry, before I let me go back. Okay, so what I really want to compute is R ijkl at P, okay, which is obtained from the endomorphism by lowering the index. So that is GLA times del I gamma jk A at P minus del j gamma ikl at P. Okay. All right. So now let me compute what these things are. So again, the first term in the expression is basically GLA times gamma del I of gamma jkl. Okay. So to compute this, recall a formula for the Christoffel symbols. So recall that sorry, this was A. Recall that this is given by half GA upper AB times del G BK by del XI plus del G sorry, let me rewrite this. So this is given by del G BK by del XJ plus del G JB by del XK minus del G JK by del XB. Okay. So at P, if I calculate the derivative of this Christoffel symbol, well, by the product rule, I can first hit the derivative on this inverse metric terms, but then by this discussion that we had, if a derivative hits the components of the inverse of the Riemannian metric, then those things are 0 at P, right? So by the product rule, I directly will get something like this. I won't hit the derivative on GAB because that gives me 0 anyway. So I'll have something like this, okay, times you hit the derivative on GBK by del xi del xj plus del squared GJB by del xi del xk minus del squared GJK by del xi del xb. Okay, but now here you are summing over a common index A. So because these are inverses of each other, this entire term is actually equal to delta LB. Okay. So now when you are summing over the index B, which also is repeated here, right. So when you sum over B, the only non-zero contribution is going to come when L is equal to B. So this formula now simplifies. This is equal to half. So wherever you find B, you replace that with an L. Okay, so that's our formula for this term. So similarly, the second term also has a similar formula. So the second term is of this form. So again, wherever there is a I, you replace it with a j. Wherever there is a j, you replace it with an I. So you get the same sort of formula. So del squared G LK del xi del xj plus del squared G IL by del xj del xk minus del squared G IK by del xj del xl. Okay, and now just subtract the two. Okay, so if you sit with a pen and paper and actually subtract the two, you will see that that these two terms sort of cancel, and what you are left with is exactly what exactly gives you the formula that I am claiming. Okay, so this completes the proof of the lemma, and now you can use the lemma to prove the proposition. Okay, so at the end of the lecture, I want to prove another nice property of the curvature tensor, namely called the differential Bianchi or the second Bianchi identity. Okay, this says the following, and we are again going to use normal coordinates. So this will really drive home the point of how useful normal coordinates are for calculations. Okay, if you don't use normal coordinates, you will have I mean already the proof looks sort of complicated, but if you don't use normal coordinates, it will be a tremendous mess that will be very hard to handle, right. So normal coordinates provide you a very useful computational tool. Okay, so what does the differential Bianchi say? This says that for all vector fields x, y, z, w and a, so 5 vector fields, you have the following. So if you take the Rm tensor, it's a 0,4 tensor, so you can calculate its covariant derivative in the direction of A. That will be another 0,4 tensor, and now again you cycle through the this and this. Okay, like in the algebraic Bianchi where we sorry, this should be Z and W. So like in the algebraic Bianchi we cycle through x, y, z, here you cycle through a, x and y. Okay, so so then you will have this and the result is again 0. Okay, so let's quickly prove this using our formula in normal coordinates. So okay, so maybe before that I should write that in local coordinates this is equivalent to the statement that del A nabla A of R I j k L plus nabla J of R A I k L plus nabla I of R j A k L, that is 0, or equivalently in terms of the 0,4 tensor, this says that nabla A R I j k L plus nabla J R A I k L plus nabla I R j A k L is 0. Okay, so let's write down a proof. Right, so so recall that that firstly in normal coordinates, if you compute at a single point P, then at this point P is simply the usual derivative plus some terms involving some zeroth order terms involving the Christoffel symbols, but because we are working with normal coordinates, this is 0. So at the point P, this is just like calculating the usual derivative. Okay, but on the other hand, we had a formula for R I j k L. Okay, what was the formula? The leading terms were given by this. So this was the lemma that I just proved, plus something involving terms that are quadratic in the Christoffel symbols. Now suppose you compute the regular derivative of this, and at P, remember I'm using normal coordinates at P, right? So at P, then of course that's going to be del A del I of gamma j k L at P minus del J minus del A del J of gamma I k L at P, plus terms where I mean it's a quadratic term, so by product rule when you take a derivative you hit the derivative on the Christoffel symbols times some other terms involving the Christoffel symbols, right? So schematically this is not an exact formula, but schematically it will be of this form, right? So now if you plug in P, then this guy is 0, right? So this implies that at P you have the following simplified formula, that del A R I j k L at P is given by del A del I of the Christoffel symbols minus del A del J of the Christoffel symbols. Okay, but now you can do the same for sort of cycling through A, I and J. So the next term that you want to look at is del J R A I k L. So that is just going to be del J del A gamma IKL minus del J del I gamma AKL, again everything at P, so yeah, maybe I should write this down a bit more cleanly. So this is at P minus del J del I of gamma AKL at P. Similarly, the final term that you want to look at is del I R JAKL at P. That will just be del I del J gamma AKL at P minus del I del A gamma JKL at P. Now, if you add all of these, you will see that you will have various cancellations. So, let me start marking out what cancellations you will have. So, firstly, these two terms will cancel. Then you have a del A del J. So, this term will cancel with this term. And finally, this term will cancel with this term. So, in the end so adding the 3, you get 0, and that is basically what was claimed in the differential Bianchi. Alright, so that completes the proof of the differential Bianchi, and hence of the important properties of the curvature tensor and the curvature endomorphism. So, in the next, in this lecture already you must have seen how useful normal coordinates are. They simplify calculations a lot. In the next lecture, we will look at some more properties of the curvature tensor, and then we will also look at what are called as flat manifolds. So far the analytically it is clear what the curvature tensor is. It measures the lack of commutativity of derivatives when applied on tensors, right. But geometrically it is not really, this is a very complicated beast. It is a 0,4 tensor, the curvature endomorphism is 1,3 tensor, so it is a very complicated object to understand. On the other hand, if the curvature tensor vanishes, we will then in the next couple of lectures we will derive a nice geometric consequence of that, right. So that will at least make the curvature tensor a little more palatable, okay. And then after that we will introduce this notion of sectional curvature, which is sort of a more down to earth version of the curvature endomorphism and the tensor. Alright, so that is the plan for the next few lectures, but maybe that is it for this lecture. So thank you for your attention, and I will see you in the next lecture. Thanks.